Okay, let's continue. And here comes our next talk, brought to you by Andrey Zubkov, who will tell you about using a GiST index in solution of custom search problem. Hello, everyone. So, this is not my typical role because I am a DBA, but oddly enough, sometimes we face problems in applications that are supposed to be solved by developers. Sometimes we, DBA, are dealing with such problems. I am from Palma Technologies Group, and I will tell you about these things. So PostgreSQL is scalable. On PGConf, we hear that Postgres is extensible, is scalable. I will show you how this can be done, but not in details because I'm not a developer. And also we'll be talking about GiST not as an index but as a carcass of how we can deal with a custom search problem. I will try it and show it to you on a real example. But of course I will not give you all the details, and I'm going to use the GiST as a functional index. So what about the task itself? Let's say we have a large amount of text. So it was around 4 million text on natural language, and we get new text coming on. And at the same time, the text can be a duplicate with some modifications, small modifications. So that was the task. There can be some paragraphs to be replaced. There could be some typos or something like this. And we need to find these repetitions. We get a new text, and out of this array, we have to find such changes. What can we use? What if this is a full text search? But it's not the case because in full text search, queries are short and accurate. It's either we are looking for something or we just say what we don't need, and we are looking for specific things. We can specify specific lexemas or relations between these lexemas. So we have a criteria. So even if we have some mistakes, full text search will deal with it. Our task is we have the same text but with some modifications. So it's not the same. So basically, in search query there are no mistakes, but we do have them. There will be some changes for sure. And also, we will find for specific lexemas, but we are looking for the entire text. So that is why we cannot use full text search. Then our developers decided to go to Stack Overflow. They found PGTRGM with indexes. This extension is great. They took it and they started to test it, and everything went well. They have created an index. This is the example of how to create index with TRGM support. PGTRGM splits the text into trigrams, and then it applies indexes to find what you need. And also, these trigrams allows you to look for the similar texts, which is very interesting for us. So looks like everything is okay. The database size is 5.5 gigs and the index is 9.5 gigs. It's because there are a lot of trigrams and everything must be indexed. So I didn't have a lot of time to go deeper into it, but I assumed that in this array of text there were some text like a white noise. It contains some binary file or something like this, and the number of trigrams just was too much. But that's okay. So here comes the query. We see that it went according to the index. It's a similar text search. It is using index. It went to the index. It captured 1 million to 200,000 blocks, and it took around 26,000 milliseconds. it was okay, but the performance wasn't okay. Given that the machine itself was full of resources and it wasn't loaded at all. So it doesn't work. Well, it works and it's good. We made a very good conclusion that trigram approach went well, so maybe we would use this one, but in a different way. What comes next? We look at GiST. Well, I'm lying a little bit because we go for Harbor and we read some Yegor Rogov articles on indexing, and we need GiST. So that's why I will tell you a little bit what is GiST. Here you can see a link to Yegor Rogov's article if you are interested about it. So GiST is a generalized search tree which is balanced, and in leaf node each record has a predicate that satisfies indexed value, and inside the tree there will be a link to child nodes and a predicate that matches with all records underneath the node. By using this GiST, you can use a consistency check. If everything is consistent, we go deeper by using our index. If not, well, we don't go for it. By using this feature, you can index anything you want, and you can come up with the required operators that will enable you such a hierarchy structure. It's not just a B tree, it's about any structure you need. So just to imagine, I got this picture from Yegor's article, how GiST indexes geographical data. So these are Russian airports on the map, and how GiST indexes them all. It's a high level of index. You can see two entries with two overlapping rectangles. Each rectangle is a predicate, and this predicate should have all indexed points. This is the high level of index. Then these rectangles are divided into smaller rectangles. Each of them is a predicate, and then so on and so on until they become just too small. By looking at this beauty, you probably want to say that our task is all about it. We are looking for a text. We do have some similarity between those texts, and we want to use this space search somehow just to accelerate this process, and we use GiST in order to do so. But we have to divide text across the space somehow. But Telegram approach was okay too, and this is to be noted. So ngram worked well. Everything was indexed. So what if we use n-grams? We take a text, we take some n-grams, so this is not a complete list because we just don't need it. So just a few of them. Each n-gram with its frequency, how many times it was captured in the text. Obviously, the list is quite big, and if we start working with all of them, it will not be very convenient because in different texts they're different, and they're actually very numerous, and we don't have to index n-grams. We have to index the text itself. What if we take these n-grams and we hash them somehow, so each n-gram goes to one of three buckets, and all n-grams will be divided into these three groups. Then for each group we will calculate the total frequency of n-grams in this text, and then we will have a three-dimensional vector. It's a very simple three-dimensional vector that we can use for GiST indexing. So it gives us an opportunity to build GiST index. So GiST doesn't support index out of the box, but there is a cube extension that allows you that supports these three-dimensional cubes. And finally, you can use GiST for your task. So we have a space similarity. And finally, we can apply what we need. We can also perform K and N search, which is very good when it comes to text search. But we have a false positive. So when we cut down the dimensions, obviously this number is not about the text, but what's important is that similar text in terms of our task, these structures are okay, and this is important for us. So what do? We write 80 strokes, 80 rows on C language to build these profiles. So the first implementation was on SQL because we just had to test it. But when it comes to indexing of 4 million texts on SQL, it was just terrible. So on SQL language, the query took 21 hours. So obviously we had to find just an 80 string function on C, and then you could use it as as a Postgres extension. So 30 rows of the code gives us an opportunity to use one pass of indexing to build this vector. Then we wrap this vector into tip cube, and we build an index.
It takes 2 minutes 20 seconds to build an index, and it has size of 1 GB, slightly less than we used to have. So what goes next? And then it's simple. Then we fix the first kind mistake, first kind error. We remember that PGRT worked well and it made everyone happy what it finds there, and then we can apply it then. First, we are going to reach the text using the index that will be close to a certain margin. So it says 60 there, but we can put more without any substantial loss in performance. And then among the things that we found, we're going to take the text with the vicinity of the similarity function from the extension of PG, or that will make us happy on the distance in the understanding of PGRT. It will sort out all the tags that do not correspond to our query. It takes 100 milliseconds to perform this search compared to 26 minutes, and it's going to take only 16,000 blocks as compared with the millions. So what do we have? A relatively compact index? Well, relatively, because for 5 GB table, a GB of index, well, maybe we could have made it smaller, but we can play with the dimensions. So I took 12. I thought that was enough. It was enough. Maybe we could have made it smaller, and maybe it would have been enough. So we just didn't have a lot of time to check it all. The lack of the dependency from the size of the text and its content, what is that? It's clear that if we index n-gram and the words and some lexemes, then the longer the text is, the more objects that we want to index will be part of this text, and it will be more difficult to work with this array. And by the way, the case with the binaries that could come with the white noise is going to really hurt us. There will be all the n-grams that it will find, and there will be a lot of it. But we don't care here that we can just break anything that we got into our 12 pockets, and we will put it into index, and we will be happy with that. And the quick index creation, it took just 2 minutes something to create for 4 million. So that's my thanks to Igor Rogov for the work he's done, and in particular about the index articles. And I would like to thank Alexander Kuznetsov, who helped me with the C language functions that I didn't have time to learn. Well, I think I'm done, and I guess so. It didn't take more than I expected and than you expected. Any questions? Good afternoon. I've got a question about about the dimension that you compare if it's not more than 0.6. This one? Yep. And then if we have one text with 50 paragraphs and the other text is one paragraph of the same paragraph, then it will not go through. Of course not. But nevertheless, then it will be really a similar copy of one paragraph. Well, that were we vulnerable, but that wasn't the intent description. We are not supposed to find separate paragraphs. We need to find text that will be exactly the same and with the same content, but there will be some parts of it replaced or changed. I think that it was done so that it was possible to somehow to hide it, to make it more difficult to see that it's a repeat. But I'm saying that point 6 parameter it could be varied, and this thing it would be found by this engine because in our index it wouldn't be possible to find it because it's gonna have completely different numbers, and the text that would have 50 paragraphs and the text that would have one of these 50 paragraphs, there will be totally different spots in space, and the GiST wouldn't be able to find those. A simple question. Function, can you share it? I had only 20 minutes for my speech. I would have shown it to you, but it's nothing special. Maybe somewhere in a GitHub, or we can take a look. It's a very useful tool. Well, nothing that useful. It's useful for us. Well, just find me in a hallway. We can talk about it. No problem. Any other questions? Okay, then let's thank Andrey for his speech.